Hi, welcome back. In this lecture, I want to talk about quantum states. Concepts of quantum state is very important, and we're going to use it to implement a bit and a quantum bit on quantum computers. So each state will be a different state of our bit. So we are going to look at two simple physical examples to illustrate the basic machinery of quantum states. The first one that we're going to look at is a system with the particles that can be only at the determined position. So we will have a number of quantum states, n number of states. So this is the quantum particle confined to a set of discrete position on a line, so only one-dimensional. The second example that we're going to look at is a single particle spin system that has only two states. So only two quantum states, up and down. So let's start with the first example. So the first example that we're going to look at is the particles that are confined on a 1D discrete geometry. In this case, let's consider a subatomic particle. So why subatomic? Well, we choose a particle that is subatomic because it satisfies the rules of quantum mechanics, right? So it's not a particle that is moving on a continuous space like a classical physics, but is a quantum particle. So it obeys to the rules of quantum mechanics. Also, we assume that the particle can be only on different states on a line, so that is 1D geometry. Because the particle obeys to the quantum mechanics rules, it can be only on points that are equally spaced. So it can be either in x0, x1, or xi, and then we have n of these points. So that means that our particle can be in one of these n states. So the space is divided in a discontinuous manner. There is a grid spacing, dx, and the particle can be found only on these particular points. So we cannot find anything like that, like here in the middle, but only on these discrete points. And because of, and this is because of this particle obeys to the quantum mechanics rules. So obviously, if we have many of these points, so that means that n is very large and the delta x is very, very small, this is a reasonable approximation of a continuous system, because x0 will be very, very close to x1, right? And then very close to x2. But still is a discontinuous system because it's a quantum. A very important slide for this course is the way that we are going to express our vectors in quantum computing. In order to express our vectors, it can be a row or a column vectors, we are going to use the so-called bracket notation, of bracket in short. So this is nothing difficult. Let's see, we have a vector v that is a row vector that can be easily expressed in this way. So we have a bracket, square bracket, and then we have each element of our vector, so from v0 to vn in a square bracket. This also can be expressed in this way using the so-called bra notation. So this is, if you see this before in quantum computing, this is nothing else than a vector using the bra notation, and this vector is a row vector. We can also use the cat. In this case will be v, and this is a cat. In this case is a column vector. So you see here a transpose sign. That means that this is just a column vector. So u0, and then dot dot dot, and then we have u n. So this cat is nothing else than the column vector. So these are just fancy words to express row vectors, the bra, and column vectors, the cats. So we will see all over the course the use of bras and cats. Nothing to worry about, it's just a way to call row vectors and column vectors in quantum computing and in quantum mechanics. So let's go back to our one-dimensional system, that is a quantum system, that require us to find particles only on a discrete point of our grid. So what we're going to do is to associate each point to a particular state of our system. So our particle can be zero in one of these n point. So we're going to associate to the current state of the particle an n-dimensional complex vector. So our vector is a row vector, so this will be bra, and each element of this row vector is a complex number. So from C0 to Cn minus 1. So we have n elements in this complex vector. The particle at the point xi is denoted as xi using the Dirac bracket notation. To each of these n basic states, we shall associate a column vector. So the column vector is a cat. So let's see. So if our particle is in the x0 position, then we can express using this cat, that is a column vector, where we put an n in the first position. If our particle is in the position x1, then we will be in the state cat x1, that can be easily expressed as a column vector where we have a 1 on the second positional vector that corresponding to x1. If we have the particle in the last position of our one-dimensional system, then the state of our quantum system can be expressed by a cat vector, where we have 1 in the last element of our column vector or cat. So let's look at more into detail to the quantum state. So there is experimental evidence that the particle can be in a strange fuzzy blending of different states. So that means that before actually measuring, there is undetermined states where the particle can be in a different states. This is called superposition states, because there's a kind of mix and blending of different states. So this is experimental evidence that, and that's how the quantum system works. So this is kind of counterintuitive, because classical physics is what we are used to. We are not a quantum particle, so for us is something counterintuitive. What is it happens at the quantum state level? So quantum mechanics make a bold leap by saying that all vectors in the complex space, right, of dimension n represents a legitimate physical state of the particle. So we're going to a complex vector to represent this blending of different quantum states. So an arbitrary quantum state that we denote as cat psi. So we are using this Greek letter psi. That is a linear combination of different quantum state x0, x1, and x until xn minus 1. By using a suitable complex weight from C0 to Cn minus 1. So these are the so-called complex amplitude. So the important part of these slides is this final equation here that basically tells that a quantum state called psi can be represented by using different quantum state, x0, x1, x and minus 1. A linear combination of this state where each weight of the state is expressed using a complex number that is also called a complex amplitude. So we said in the previous slides that every state of our system can be represented by an element of the complex set of dimension n in the following way. We take our ket psi. This is a column vector where each element is a complex number. So this is, notice here is a column vector because there is a transpose, right? And each element of this vector is a complex number. We say that our state psi is a superposition of the basic states. What are the basic states? Well, the basic states are the x0, ket, x1, ket, and then dot, x n minus 1. So those are the basic state. So we can express this as a superposition state. What we are going to do is to use a linear combination of this basic state, and we applied the different coefficients C0, C1, and then C n minus 1. So psi represents the particle as being in all different pure states location or a blending of these pure states. In fact, there are different possible blendings, but let's look at more into detail how this complex amplitude works. The quantum mechanics tells us that the complex numbers C0, C1 till to Cn minus 1 tell us precisely which superposition of our particle is currently in. What this doesn't mean? Well, this means that the norm square of the complex number Ci, that is an element of our vector, divided by the norm square of psi elements, will tell us the probability that after making a measurement or after observing the particle state, we will detect the particle at the point xi. Right? So let's go back to what it is C0, C values, these complex values of our column vector tell us. Well, these are basically telling us what is the probability of observing a certain state after we did a measurement. Before the measurement, we have our vector. We have our vector that tells the probability of observing in one of the n quantum states. Right. So this is Slicky. Is an expression that tells us what I just say in words, the probability of finding a particle in the quantum state xi, that is one of our grid points, is the square of the amplitude of the complex number, or the magnitude of the complex number, divided by the norm of all the vector that is also being squared. So notice that the pi is a probability, so this is always a positive real number, because we are taking the magnitude of a complex number that is a real number, and then the norm of a square norm of a vector that is also a positive real number. So pi must be a number. And also because we have this normalization here at the denominators, this number is always between 0 and 1. So it's really like a probability. So I told you that before actually the measurement that we indicate using this wavy arrow line, the quantum states can be in a superposition, but after the measurement, we will observe only of the possible quantum states. So let's see an example in practice. So we have our quantum state that we denoted as a ket vector, that is our psi. So this is a column vector, and we have 4 elements. So our particle can be only on 4 different positions: x0, x1, x2, and x3. Right? And each of these numbers tell us the probability of finding the particle in one of these 4 positions. So if we take this number, we take the magnitude, and we take the square of it divided by the square norm of this vector, we will find the probability of finding the particle in the x0 position after the measurement. So this refers to the probability here. This number here probability refers to the probability finding here. This number refers to the probability of finding the particle in position x2, and then finally this number refers to the probability of finding position in this discrete point. So as I told you, the first step is actually to normalize. So this, if you take the squares sum of the amplitude of these complex elements is now equal to 1. So we need to do normalization first. So we take our psi, so we take the norm, that is 4.3. If we want to find the probability of finding the particle in the position x2, that is this one, we are taking this number, I, we take the magnitude, we square, and then we divide it by the square norm of all vector, and this is give you this number here, the 0.05. That means that the probability of finding the particle in this position after we did the measurement is 5%, right? And you can find the probability of finding the particles in any of these quantum states by doing just this trick. So we're going to change it here. Instead of I, we're going to take a different complex number here. So this is quite simple. So the important part is that before the measurement, our particle is living in these blending quantum states that it can be in a different state but with different probability. And each of these elements, it tells us the probability of finding a particle in a certain quantum state after the observation or after the measurement. So we always deal with the normalized states. The sample that we saw before was not normalized, so we did a normalization ourselves. So this is an important part. Always work on normalized state. If we realize that our vector is normalized, we should do the normalization. Let's look at a system that has only 2 quantum states. In the previous quantum system, we have an n number of quantum states. That is where we can find our particle. So let's look at a simpler system using an electron, the so-called single particle spin system. So this is inspired by the Stern-Gerlach experiments that consisting shooting a beam of electrons through a magnetic field oriented in a certain direction. So we have a gun of electrons, and then we let going through a magnetic field. So this is a simple dipole, and we go this, and we see that this experiment is show that an electron in presence of a magnetic field will behave as it were a charge spinning top, right? It will act as itself as a small magnet, and try to align to the external field that we have here. So the field will actually split the electron beams in two streams with opposite spin. So one going up and one going down. Right? Depending on the spin of the electrons, will go up or down. So we will, the electrons will align with this external magnetic field. So certain electrons will be found spinning one way, so we'll go, for instance, up, and certain others will spin in the opposite way, so they will go down. So in this case, we are going to have electrons only in two quantum states, either spin up or spin down, where basically observe the two beams hitting the screen at the back after our magnetic field. So for the vertical axis, we can have a spin up, and we can use this cat with the arrow going up, and then we can represent the quantum state for the electrons going down with a spin down using arrow down and then cat. The generic state will be a superposition of spin up and spin down, or psi, and then we're going to have the basic state, that is spin up and spin down, multiplied by the complex amplitude C0 and C1. So just like before, C0 is the amplitude of finding a particle in the up state, and similar, C1 is the probability of finding the particle in the down state, so the spin down. So this is very nice example. So for instance, if we have a bit or a quantum bit, that is the quantum formulation of our bit, we can use this system, right, where we can use up and down. Obviously, before any measurement, our bit can be in two states, but when we will observe just either 1 or 0 up or down. But we will come back later when talking specifically about quantum bit or a qubit. Just to finish up with this lecture, I want to give you a simple example on finding the probability of finding spin down. So for instance, consider a particle whose spin is described by the cat. So our quantum state is a superposition of the two states, spin up and spin down. And then we have a complex number that is telling us the probability that is related of probability of finding particles either in spin up or down. The first step that we're going to do is to find the norm of this spectrum, because we want to do the normalization. And then we can find the probability of finding the particle in the electrons in the spin up by taking this number. I take the amplitude, so I take the amplitude, so this is 3, so square, so it's 9, and then 4 is 16, so is 15, and then we should take the square, but also we should we take the square root, but then also we take the square of the square root, so this number is actually 25. And then we divide it by the square of the norm. So we have the norm of the full cut, this one. We take the square, and this number is 0.32. That means that the probability of finding our electrons in the state with the spin up is 32%. We can do the very same for try to find the probability of finding the particles in the spin down quantum state. We can do it either way. So we can, since we have only two states, we can just say 1 minus the 32, or we can calculate, just take this complex number. That is the way around here. And the probability of finding our particles after the measurement in the spin down is 68%. So this is the last slides, and the next lecture I will talk a little bit more about quantum bit. We saw that we already talked a little bit, but we go more into detail on how to use quantum states to describe a quantum bit. Talk to you soon.